My name is Stefan Conrady. I'm the managing partner of Bayesia USA. And beyond my admission that I know nothing about agriculture, I should also fully disclose that I'm working in the field of artificial intelligence with a company named Bayesia, and we're developing software in this field. So the things that I'm going to share with you somehow relate to our specific technology that we present, promote, and sell. But I hope that the content of my presentation is relatively independent of the specific things we do. So please don't take this as a sales pitch. Even though you may not have heard of Bayesian statistics or Bayesian networks, it's actually becoming very common, practical in use across a very wide range of domains. And here I'm highlighting a few of our customers that have been using Bayesian networks and Bayesian statistics. And as you can tell by the logos, it's really a wide range of companies representing a wide range of problem domains, everything from cancer to research to military strategy. You name it, Bayesian networks are being used. Now, as I'm talking about several examples, just a few examples about the application of Bayesian networks, I will cross-reference my recent book. It's available for free download. Now, Bayesian statistics or Bayesian networks is still a fairly narrow field, but we've been actually very pleased. We've had over 10,000 downloads of this book, and so I hope that helps to promote the awareness and the understanding of practicality of Bayesian networks. So now, of course, this is a very tough act to follow for a number of reasons. First of all, Ron's presentation was fabulous, and I felt he spoke from my heart. So this was brilliant. And secondly, I'm standing now between you and lunch, so I'll do that. Now, you probably hear this a lot. People are talking about big data analytics, advanced analytics, machine learning, artificial intelligence, and your management is talking to you about, well, all the data you have. They're investing hardware, infrastructure. And so there's perhaps this impression or this understanding that big data is just about pushing away all other forms of research, and that there may perhaps be little room for traditional theory as you may have learned it in your respective problem domains. But the problem is with big data, the biggest problem is that we don't always have big data. What if we have little data? What if we have no data? Then what? So I want to talk today about small data challenges. And there are actually two angles I want to take. One is fairly obvious. The problems we encounter typically with small data, and that is generating knowledge from small data. And there are things like over-parameterization, variable selection issues, and so on. Those are fairly well known. But I also want to talk about the difficulties of applying knowledge to small data. Because when we build models, whether it's a predictive model or a causal model, and then we have to perform inference with new observations, these new observations that we may obtain may be incomplete. They may be uncertain. Sometimes we just want to, with the knowledge that we've generated, hypothesize about problems and scenarios. Another thing we need to take into account, acquiring observations is expensive. Think about a doctor who examines you, taking the blood pressure is relatively inexpensive, whereas a full body MRI scan is very expensive. They provide different amounts of information, and we need to figure out somehow how can we prioritize the acquisition of evidence. And so that's what I will be talking to you about today. But before I jump right into sort of all the technicalities, I want to frame things up a little bit because there are so many buzzwords out there. We have heard this morning about regressions, about random forest, decision trees, big data, and I just kind of want to get this organized, and perhaps that will help us position some of the new methodologies I'm going to propose. So my starting point is a paper by Galad Shmueli, and she wrote this about 6-7 years ago, and she's talking about how we need to very carefully distinguish between the purposes of models. And she said a big challenge in statistics is, and I think it's emerging as a problem that is perhaps as big as the misunderstanding of p-values, and that is that scientists conflate predictive models with explanatory models with causal models. Because nowadays it is actually so easy to build good predictive models with machine learning techniques and all these tools that are out there, and we fall into this temptation that we take a predictive model and interpret it in an explanatory way. So I want to kind of expand on that, and perhaps you have sort of seen that progression of insight on Dan's invitation. I'm proposing an x-axis for model purpose that starts with description and goes to prediction, explanation, simulation, and ultimately optimization. And perhaps I should use my laser pointer so I can avoid the wild hand gestures. Oh yeah, here we go. And in the most general sense, it's a spectrum that ranges from association to causation. So that's my x-axis in my proposed map of analytic modeling. Now, secondly, the question is, where do models come from? Traditionally, we've used theory. We have hypothesized about a problem domain. We thought about how things work. We've specified a formula. And then perhaps we've used some data to estimate parameters. Nowadays, we have data coming out of our ears. So there's all this data available. And through machine learning and artificial intelligence, we can now often generate models automatically. So let me now put these two things together: x-axis model purpose, y-axis model source, and we can think about, which types of techniques fall onto this map. And perhaps kind of the hottest topic these days, closely related to big data and advanced analytics, is artificial intelligence. And when we read about it, there's this enormous expectation as to what artificial intelligence will be able to do for us. Now, however, I'm afraid I have to tell you, artificial intelligence, as great as it is for many purposes, it is also very, very limited in what it can do for us. Because I've put it here in this upper left-hand corner. Very clearly, artificial intelligence is mostly driven by data, but you see it's positioned on the very left. What I'm saying is artificial intelligence, machine learned models, for the most part, cannot be used for explanatory or causal purposes. So you are restricted really to building predictive models. Artificial intelligence can build fantastic predictive models. Think of neural networks and many other techniques that are out there, fantastic predictive models, but for the most part, you cannot kind of look inside and interpret them. You cannot open up a neural network and open the box and see what's happening in there. So we're kind of locked into a corner here. Also, what is challenging with artificial intelligence is how to bring in theory, how human knowledge, human intelligence, as opposed to the artificial intelligence. So kind of this bottom corner here. What I'm going to propose is that there is actually a framework, a paradigm that can really bring together, if you will, the best of both worlds. And that's Bayesian networks, because Bayesian networks have the ability that they can be learned from data, so we can machine learn, machine generate a network structure. And on the other hand, we can take our expert knowledge, our domain knowledge, and encode that manually into a Bayesian network. And from that, we can jointly represent machine learned knowledge and human knowledge, human expert knowledge. And the addition of human knowledge gives us also the ability to introduce causal knowledge, which is one thing machines can still not yet discover. It's kind of the holy grail of data scientists to be able to discover causality, but to this date, that is not possible. You know, there are a few ideas out there, but my colleagues certainly have kept searching for decades to no avail. The introduction of human knowledge allows us actually to extend a Bayesian network and utilize it for causal inference. So that's a very big topic, and I think a major, of great importance. However, today we won't be talking about that. Actually, I have a 4-hour seminar just on that topic alone. And actually, we have a 2-day course on that topic alone, so I'm not going there. Rather, what I want to focus on is sort of the left half of this map. I want to share with you 2 examples. And the first example being about knowledge encoding and diagnosis. And if you will, the small data part about this is actually, in this particular example, we have no data. We just have expert opinion. And then we have unreliable evidence. So we're kind of in very shaky ground. But what I want to show is, even though we have these vague assumptions, these weak observations, we can still reason about this problem domain appropriately. And then secondly, a slightly different problem, there we have data, actually a fair bit amount of data, far short of big data. But there I want to share with you how we can discover knowledge from data, build a predictive model. And again, as I said earlier, building a predictive model nowadays isn't rocket science. What I want to show here is how we can perform inference with just a few pieces of observations. I want to show how we can use a Bayesian network predictive model to help us guide in which sequence we should seek new observations to kind of diagnose the patient in that case. So this will be about small data and incomplete data. Now, and by the way, since I'm just blabbing on here, please do feel free to interrupt me and ask questions. I don't want to just, as Dan said, I don't want this to be a lecture. Bayesian networks, that's a new paradigm. It's actually not all that new. The Bayesian network paradigm was introduced or invented by Professor Judea Pearl, a researcher at UCLA who has most of his life spent on, as he says it, mathematizing causality. And his first seminal papers came out in the mid-1980s, and since then it has grown into a fairly large field of study with many, thousands of papers that have been published, many books that have been written. And what I'd now like to do is connect Bayesian networks to what you have probably heard, and that is Bayes' theorem. And sometimes the concept of Bayesian networks and Bayesian statistics gets conflated, and I kind of want to clarify that a little bit. So let me start with Reverend Thomas Bayes, a Presbyterian minister in the south of England, who was a hobby mathematician. And his deep insight, what we now know as Bayes' theorem, wasn't even published during his lifetime. Rather, a friend of his discovered it in his papers, and it was published posthumously. And it is still what we use today in many applications, and that is basically Bayes' theorem. This well-known formula tells us how we should update our beliefs given new evidence. That's what we want to talk about. And I think the example that Ron made earlier with being hanged given that I'm dead versus the probability of being dead given that I was hanged and so on, this back and forth, this inverse probability, this is exactly what can be computed with this formula. But let me now link that to the concept of Bayesian networks. A Bayesian network is a probabilistic graphical model which means the graph is the model. There are no equations, there are no formulas. A Bayesian network just consists of two components. It's very simple. It consists of a node and an arc, or nodes and arcs. And the way I'd like to illustrate this is with actually quite an old example about Bayesian networks. This was first written up by Lauritsen and Spiegelhalter in 1988. And this story is about a specialist in respiratory medicine, a lung doctor, who wants to summarize his knowledge about his patients. And so he looks kind of a little bit older, perhaps he's about to retire, and wants to pass on his domain knowledge to his successor. So he's starting to encode variables about his patients. So he starts with the first node, and variables of interest are called nodes in the Bayesian network framework. And this first node is age. And the node age has 3 discrete states. And each state has a value here, under 30 years of age, 30 to 65, and over 65. In addition to the state values, there is a probability that is associated with these states, 25, 40, and 35%. Now you may ask, well, where do we get these probabilities from? They could come from domain knowledge. He just happens to know that because you perhaps have a feel for the proportions and the age distribution of your patients. Or perhaps you simply count the patient record and thus arrive at the probability distribution. So that's the first node. And now we will be introducing a second node. And that node, he's a lung doctor, so it's perhaps appropriate. This node is about whether a patient is smoking or not. So this is a binary node, just true and false, once again with a probability associated with it. Now you'll say, okay, this is not particularly interesting so far. Now we are introducing an arc. And this arc now relates the states of the node age to the states of the node smoker. And that linkage is probabilistic. So we can now see here, given that a patient is under the age of 30, the probability distribution or the probability of this patient being a smoker is 69%. So you may ask, well, gee, I can represent this as an Excel spreadsheet. I perhaps don't need Bayesian networks for that. It becomes more interesting when you actually bring together more nodes than that. So beyond the age and smoker, here we have introduced bronchitis, dyspnea, which is shortness of breath, tuberculosis, and other lung-related diseases and tests and exams. And when you look at this network, you have to think about it behind it. Wherever an arc connects to a node, you have a conditional probability table that tells us how these nodes are connected probabilistically. Now, what is this good for? It's actually quite remarkable what can be achieved with this type of representation. And I want to take you through a few of these properties. The first interesting property is that you're modeling all variables simultaneously. So you don't have to distinguish between a dependent and many independent variables. Just all nodes, all variables are created equal. And numerical and categorical variables coexist peacefully in a Bayesian network. So let me perhaps just becomes a little bit more apparent if you look at a regression, for instance, an algebraic formula where you would very clearly have a dependent variable and typically multiple independent, one y, multiple x's. And along with this representation, Bayesian networks allow you to perform inference in all directions, which is not possible in a typical formula, in a typical regression. If you look at this regression, you know exactly that you can only set values for the x's and then obtain an estimate for y. But it wouldn't work the other way around. In a Bayesian network, you can do precisely that. You can set a value on any node, and then read out the corresponding distributions for all the other nodes. So my background is really in the car industry, so I always try to bring things back to mechanical analogs. I liken this to this set of gears, because if you look at these gears and how they are connected, it wouldn't matter where you provide the input torque. I could start cranking here or there. The motion would go through the gears, and I would see all of them moving. And this is exactly what is happening in a Bayesian network. You turn kind of one gear, and everything propagates, and you can see it. So, but that's not all. I already touched on the fact that Bayesian networks are probabilistic, which means the way I enter evidence into them and read evidence from them is via probability distributions. And this is very attractive because a lot of the things we deal with are uncertain. Think of sensor data. There are so many observations that we assume to be sort of single point values, but actually are not. And so with a Bayesian network, we can very directly work with that. Yes, and this is the most important part. And that was really the driving motivation behind inventing Bayesian networks, because Professor Judea Pearl realized that algebra is very limited in how it can express causality. Think of this formula: Newton's second law of motion. Acceleration equals force divided by mass. Or, to quote Newton's definition verbatim, he speaks of acceleration being produced by the force. So in this case, this formula very much has a causal meaning. Yeah? So here we have a causal interpretation is possible or even mandatory. So now think about if we solve this same equation for mass. It looks like this now. But we can immediately know, but you can't produce mass, at least in sort of classical mechanics. I don't know how it works in the world of quantums, but here very clearly that is not, a causal interpretation is not possible. But just by looking at the equal sign, you wouldn't know. You would have to either footnotes or commentaries and so on. Now, in a Bayesian network, you can very specifically encode the causal assignment through the direction of the arc. And so let's now take that and go to our network that our doctor has produced. I can take this network, and I won't talk yet how that was generated in particular. I'll just take it as is. I take it as a piece of knowledge given to me, and I can now perform inference. The first piece of inference, or first... Yes, please.
What do you mean, like, according to your definition that you had earlier, what do you mean so you measure the probability of acceleration given mass?
Mm-hmm.
What do you mean by that?
Say it again, please.
So maybe we should go to the Bayesian network, right? Right here. So you said like when you build this graph, if you
mm-hmm.
like, then you're measuring the probability of one node given the other node, correct?
Yes.
Okay.
But not only. You can encode your probabilities or estimate them from data, plus you can encode any causal direction.
Okay. So what does it mean for you or for the network or for interpretation, if you like, since this is why we have a Bayesian network, I guess. What does it mean to find the conditional probability of acceleration given mass? How would you interpret that?
Well, I think in this case, it's very straightforward. You can, and this is actually what I was going to point out with the next slide, even though you may have a causal arc going to acceleration, you can still perform observational inference in the other direction. This kind of representation allows me to distinguish between observational and causal inference. So I can take that and very clearly distinguish kind of given that I see versus given that I do. So this would tell me that mass cannot be produced by force if I encoded it that way. Yeah? Let me move on to the next example and it will perhaps become a little bit clearer. So here I'm performing inference. I set evidence on a node age. I observe age. I say, okay, I'm now looking at the patient group over 65 years of age. And given that age distribution, the probability of cancer is 8% roughly, which is different than my marginal distribution for age in cancer. So marginal distribution for cancer is 4%. Given age greater 65, the probability of cancer is now 8%. Again, you could have done that with an Excel spreadsheet, so that's not a big deal so far. In a Bayesian network, I can now immediately reverse the reasoning. I can say, given cancer, what is my probability distribution of age? So now I can see that given cancer is true, now the age distribution skews older. Again, you could have rerun a new pivot table and arrived at the same. But the interesting thing about a Bayesian network is that you can perform inference in all directions. I can set a first piece of evidence, a second piece. I can set partial evidence. I can set soft evidence. And all the other nodes are updated given the evidence I enter. So what we have is kind of an inference engine. I set some nodes to some values, turn the crank, and everything gets updated. So let me show you how that works in practice. Let's go to our first example. This is a very simplistic example. This is about us encoding a piece of knowledge and then trying to perform diagnosis with it. This is an example by Danny Kahneman, or rather Kahneman and Tversky. They've written a book quite a while ago that's called Judgment Under Uncertainty, Heuristics and Biases. And there are many, many examples in there, but a lot of them are about human biases in reasoning. And one thing that they make very clear is that humans are good to reason from cause to effect. It comes very, very natural to us. But on the other hand, if we have to reason from effect to cause, that is so much more difficult. So let me try this out on you. So here's the story. This is an example taken from Kahneman and Tversky. And the story goes like this. You have a taxi cab was involved in a hit-and-run accident at night in a small city. There are only two taxi companies operating in this town, yellow cabs and white cabs. And we know how they're distributed. The yellow cab company is the bigger player. 85% of the taxis in this town are yellow, 15% are white. So now we have a witness. We always like to have witnesses. And the witness says the taxi that hit the other car and then drove off, that taxi is white. So now the question is, how do we interpret that? Of course, as always, we bring in expert witnesses. So we bring in a witness, and he says, at the light conditions that were present at the time of the accident, the human eye has the ability to correctly distinguish between white and yellow with an 80% probability. So that's his expert statement based on his research. Now, our question is, what was the probability that the taxi was actually white? So we have 85%, 15% yellow and white cabs. We have an 80% probability that the witness is correct, and the witness says the cab is white. Who thinks that the yellow cab company is responsible? Who thinks the white company is responsible? White, show of hands. White? Okay. Yellow? Okay, so it's not straightforward, is it? Yeah. The other way around, it will be very easy, but reasoning backwards from effect to cause is more tricky. Now, we could apply Bayes' rule and compute that, because we have all the pieces of information. But as you can quickly see, this becomes a bit cumbersome, just algebraically to write it all out. And you can imagine if you have 2 witnesses, 5 witnesses, and many more simultaneous conditions, that will very quickly explode your brain because you can't do it any longer. And that's where Bayesian networks are so helpful as an inference engine. So let me now encode what I just said into a very, very simple Bayesian network. Here my first node is for taxi, and I have 2 states for taxi, yellow and white, along with their probability distributions. And then I have the witness statement. And the witness statement is clearly a function of the taxi color. But we also know from our expert witness that the witness is only correct in 80% of the time. So we can encode that. We can say, given that the taxi is yellow, the witness says yellow in 80% of the cases, and so on. So I can fill out this conditional probability table. And with that, we have a Bayesian network that is ready for inference. And of course, this inference direction is very simple, because if I say the taxi is white, then we have a probability of the witness saying it is white. Now, the other way around, that's the question. That's the one we can't do in our head. And even with pencil and paper, we will soon start to struggle. So now we want to perform inference in the opposite direction. The witness now says the cab is white. Yeah? Let's compute the probabilities. So, given that the witness says it's white and the probabilities that we had originally encoded, we now arrive at a 41% probability that the taxi is actually white. So, if this was a civil trial, a civil liability issue, we wouldn't have enough evidence to blame the white taxi company. Yeah? So, and again, this is super simple. You have a question? No. Oh. This is a super simple example, but you can envision how very quickly things can become very, very complicated. And considering that, I worry how juries can ever come to any conclusion, given that all pieces of evidence that they see have only a certain degree of reliability. I know I'm running late, so let me accelerate a bit. Let me now move to the second example. So here, we don't have an expert witness who tells us what the probabilities are. Here, rather, we're now attempting to discover knowledge from data, from a relatively small data set. And then we want to see how we can best use the knowledge gained from machine learning for performing inference. And this is about breast cancer diagnostics. And obviously, it is critically important to get a diagnosis right, because false negatives in terms of breast cancer detection could have catastrophic results. So let me just cut the chase here a little bit. The background of this study, well, this is an older study by Wahlberg and his colleagues. This is about how to interpret fine needle aspirates where potential suspected cancer cells are aspirated from the female breast, and these cells are then examined under a microscope. And there's a wide range of attributes that can be examined, such as clump thickness, uniformity of cell size, uniformity of cell shape, and so on. And in this original research paper, the process was as follows, that instead of manual interpretation of these suspected cancer cells, the researchers used an image analysis program to quantify and say the clump thickness equals 5 or quantify all these measures. And all this data has formed what is now known as the Wisconsin Breast Cancer Database. So that's now widely used as a reference data set for machine learners. And what we want to do now is we want to take this original database and see whether we can discover a predictive model in the form of a Bayesian network. Yeah? Now, just to point out one thing, what is kind of challenging about learning networks, and that is the sheer size of all the possible networks that could link up the existing variables. So what I've shown here are 25 different network arrangements with just 3 nodes. So if we use the 12 nodes from the breast cancer data set, or the 12 variables, there would be 5.2 times 10 to the 26 possible network configurations. And our learning algorithm somehow has to find a good one out of these 10 to the 26, 500 septillion to be precise. I have not illustrated those. It would not fit on the screen. So what I'm now quickly going to show you is how this is done in our software, but our software in this context isn't particularly relevant. You can do this in many other ways. So let me switch gears and actually show you how this works. How are we doing on time?
Okay.
Yeah? Okay.
Is the software open source?
No, of course not. Very expensive. For academics, it's inexpensive. Commercial use is very expensive. So what I will do here, hold on. Oops. I will open the original data set, the original breast cancer database set. And there are a number of steps I need to take here about defining the variables, about how to process missing values. And we could just talk about that for several hours, but I won't, because I know everybody's hoping for a lunch sometime soon. I will more or less skip all the key steps here that are relevant in terms of the quality of the predictive model that we will ultimately produce. I'll just say I've done this before, and I'm taking the default steps here so I can get to the key point. So I'm bringing in my data. So I have now, this is nearly invisible. Okay, this is slightly better. Let me try to make this still larger. Okay, so now each variable that we had in our original data set is now represented as a node. And here in this case, we have a target now, the ground truth, because these researchers that assembled the Wisconsin breast cancer database, they treated the patients and so ultimately could establish what was truly cancerous versus what was ultimately benign. So that knowledge is contained in the node class. So I will make this node class my target node, and this allows us now to machine learn a network, a predictive model for the node class. I will go into our learning menu. And here I should say, when you machine learn Bayesian networks, you could perform unsupervised learning, basically just discovering all relationships between all nodes. Or what we will do now is to just try to learn a network that is good at predicting the node class. That's what we'll do. And there we have several subsets of algorithms. I will not go into any details here. I'll just choose what I've gotten to know as a good one. And so here we have our first Bayesian network, a predictive model of the node class. Let me just perhaps rearrange this a little bit so we can better look at what all this means. Let me turn it around. So hopefully this is somewhat visible. This is now a Bayesian network as a predictive model for the node class. And if we had time now, we could go through all the steps of validating that this is actually a good predictive model. We can perform cross-validation, or we could set aside a test sample and really establish, is this a good model? You'll have to trust me, it is. If you download our book, in one chapter we go into detail as to how we arrive at this. But what I want to share with you, and this I think is really the interesting part of why Bayesian networks are attractive for knowledge representation, and oops, pressed the wrong key here. They allow us to quantify the amount of information that is contained or that is brought by each predictor node with regard to the target node. And I can highlight many other metrics related to the information theoretic relationships between these nodes. And here, this particular case, I've decided to showcase the node or have the node size represent the mutual information that the node has, that each node has, with regard to the target node. So that can help us to basically say, well, which ones should we check first? Which ones is particularly meaningful? And here, of course, nobody can read this. I think this is uniformity of cell size, for instance. The second one, second largest, is uniformity of cell shape. But there is something interesting here, and that is the information between those two predictor nodes is also very large. In this case, uniformity of cell size and uniformity of cell shape have as much mutual information between them as they have with a target node. So this gets into the typical problem of multicollinearity, and we'd say, can we somehow get rid of one? In a Bayesian network, we never worry about multicollinearity, because if there is multicollinearity, then that's in nature. Nature has these variables that are somehow related. And if nature is that way, we should have that represented just like that in our model. So that's why we are not trying to suppress or deal with it. We'll keep that as a feature. Now, what can we do with that? Of course, we can just sort of predict now, basically by observing new data sets, like new cases. But what we want to do now is have this network help us prioritize in which order I should seek evidence. Because in many, again, medical is a perfect example, because in a diagnosis, you don't get all exam results simultaneously. You know, you start with the blood pressure, and you have a little bit of information gain. And then you do this, and you ask whether the patient is a smoker, and so on. So you probe and seek, trying to reduce your uncertainty with regard to the diagnosis. The problem is, you know, there are so many options, so many things to consider, that it is often difficult to go on the optimal path. That's where the information theoretic content that comes from the Bayesian network can tremendously help us. Because I can now, using this tool, I can run what we call an adaptive questionnaire. So this is a questionnaire that takes into account the information content of each node. Let me just bring this up here. In the right-hand panel, I'm bringing up the monitors of all these nodes. And it now tells me in the order in which I should seek evidence. So here in this case, the first thing I should check out is uniformity of cell size. And now you may say, well, it's pretty similar to, let's say, a decision tree. But the thing is, you don't always have the knowledge coming in the order in which you would ideally like to have it. So, you know, I may not have uniformity of cell size. So here, this recomputes dynamically, given what I've just observed. Now, what's the next best thing to collect? And again, with the MRI exam versus taking the blood pressure, they have very different costs and need to be accounted for. So here we could take into account the knowledge gain, the information gain, plus the cost of acquisition, of acquiring this piece of evidence. So just going through this now, I'm just saying I have observed uniformity of cell size is greater than 2.5, and now I get an updated probability. Now this tells me that the probability of cancer, given this first piece of evidence, is now close to 85%. Now I'm observing bare nuclei, and given that observation, my probability of having cancer actually goes down. Now it's below 40%, and so on. So, and I think Vasilios mentioned the concept of entropy earlier. This is all based on the concept, how can we best reduce the uncertainty that we have, in this case, the uncertainty of our target node, so we get to the best possible, to the diagnosis in the quickest way. Ideally, before we collect absolutely everything, that with the smallest bits and pieces of information, we can reduce our uncertainty and then help this patient to get to the appropriate treatment. So we can also generalize that, and sometimes, when you sit in front of a computer, that is very fine and dandy, but sometimes you may be like in a kind of emergency situation and can't do absolutely everything, in which case we can prepare something that looks very, very similar to a decision tree, which is a generalization of our adaptive questionnaire. So you can, if you have a large printer, you can put it on a wall, and it allows you to kind of look for, you start here, you read what is the first piece of evidence to collect, and then given the values you obtain, then you move on and then see kind of what's the next best piece to collect. And this is important because sometimes you may, let's say, look at this here. At this point, with the evidence you've gathered so far, that going down this branch, it looks like, almost impossible to have cancer. 2% probability of cancer. So you think patient is in the clear, but if you look ahead, you can also find out, well, which variable could now turn things around. You might be tempted to stop here, but looking ahead, it's like if there could be one variable, if that variable had a certain value, that could ruin absolutely everything and change the picture. So we can obtain that from that information. So let me briefly switch back into PowerPoint to conclude. One attractive thing about these techniques is that they can very easily be shared. So in this particular case with the adaptive questionnaire, we have the ability with our technology to publish this instantly to the web and make that available as an interactive tool, and you can literally publish this to third world countries without them having to have any kind of infrastructure other than access to the internet and a web browser. So, any questions? You were so quiet. Yeah. Yes.
I was just wondering, to the point that was spoken earlier, about decision trees and about this process. From my experience, I was kind of surprised when going into, or maybe academia at some point, to just seeing the level of knowledge of statistics as a whole by scientists is actually pretty poor. I know we don't want to say it, but that's pretty true. As an entry-level thought process of someone maybe trying to go in the direction of decision tree or a Bayesian, what level of knowledge or experience would it take to make something like that happen?
Well, I think there are two answers to that. Bayesian networks are a different paradigm, so it really forces you to rethink your traditional approach to problems. So a learning curve is required. But once you've kind of gotten over that, I think Bayesian networks are such a nice, logical, and intuitive representation of the real world that basically everything you look at starts to look like a Bayesian network. It's very easy to represent complex domains, and what I haven't talked about is manual knowledge encoding. We could now sit here and, as a group, think about any domain and say, oh, this is relevant, that's relevant, how this is related. So in no time could we collectively encode a network, including all our diverging opinions on things, and then use that network for reasoning. It's a beautiful way to merge knowledge from diverse groups. And so in that sense, once you've made the leap and embraced that framework, and it's really mathematically super simple, life becomes so much easier. So even though the terms Bayesian and Bayesian network sound scary, I kind of went that way because I thought statistics is difficult. A lot of things are not super intuitive. Reasoning with Bayesian networks I find to be much more intuitive, much more in line with human nature.
Just one quick question. How do Bayesian networks deal with interactions between your predictors?
They are recognized as arcs. So in our case, in the example that I showed earlier, we had arcs between different predictors, and these arcs showed mutual information. So that is being taken into account. So it's a great way to discover high-dimensional interactions where a single node may have relationships with 3 other nodes, and all those relationships can be nonlinear. So we don't have to specify that it's a linear or quadratic relationship. We can just let that be discovered. All right?
If anyone has more questions, one more pitch.
One more pitch, free book download. You can also get it on Amazon, but just get the free book.